Okay, let's get started. So today we're going to be covering attention mechanisms. So remember at the end of last class, we talked about one of the issues with recurrent neural networks, right? Which was the vanishing gradient problem. In this class, we'll look at a couple other issues associated with recurrent neural networks. Then we'll introduce a concept of attention mechanisms, which addresses some of these issues. We'll also look on the iPad at a more specific example of how self-attention in particular works. So this is the core building block of the transformer model, which we'll be talking about on Wednesday. So yeah, let's get started. Some logistics stuff. So your homework 0, the grading will hopefully be done by maybe within this week, who knows, we'll see. But sometime soon. The first quiz from last week is due today. You'll have another quiz due on Friday, going out either today or tomorrow. Homework 1, the next homework, will be released sometime in the next 2 weeks. We're not finished making it yet, but it should be fun. We're going to ask everyone to make their own data set, actually get someone else to create a data set using your annotation guidelines, and then you'll have to train one of these neural network models using Google Colab on the data set that you just made and see how well it does or doesn't do. Okay, and then your project proposals, the deadline for that is coming up. I don't know what the 24th is, I guess Friday maybe, or Thursday. So whenever that is, you should submit that. We'll aim to give you feedback within a week or a week and a half of that deadline. So you have some concrete changes to make if you need to, and you'll have a good plan moving forward for the rest of the semester. Someone asked about compute resources for projects. So obviously, you're not allowed to use the Gypsum GPU cluster. Right, as of now, we have, Google Colab is probably the best. It's a obviously free resource. There are services you can sign up for. I think like Google Cloud gives some free credits for new customers, so you can try that out. I'm not sure if it works with their just GPU machines, but it's worth a shot. And of course, if you have your own GPUs at home, you should feel free to use those. Someone else on the anonymous form asked, essentially, do neural networks process text, or the representations that they're extracting? Is that process similar to how we actually understand language in our brains? I am not qualified to answer this, but I'm almost certainly sure that the answer is no. Also, we don't know really how the brain represents or processes language, so that's another wrinkle in this, but you should certainly ask some cognitive scientists or psycholinguists if you want to know more. We'll do a class later on in the semester on psycholinguistics, so you can probably get a better idea then. Yeah?
Roughly, the Google Colab GPU, how good is it, comparable to NVIDIA?
So the question is, how good are the GPUs that Google Colab assigns? They have a bunch of different types, and it, I think, is still a random assignment on which one you get and how much memory within that GPU that is allotted to you. So yeah, there are ones that are quite good though. I think all of the GPUs that you can get are quite good. It just depends on the, I think they do assign multiple people to the same node sometimes, so it can vary the experience and like how much you might be able to fit in a batch or something. But you can look at all of that stuff and make sure that you got the GPU that you want before proceeding. Okay, other questions on anything? Yes?
What if during the project implementation we find out that the Colab GPU is not enough for our fine-tuning or training stuff?
You could scale down your project to smaller training data or model size to make it work. Or you could see if there's any other service that you can use with credits or something like that that you can use for free. I have tried in the past asking some of these companies to give us credits for the class, but so far I've failed, unfortunately. These companies don't care about our class. But yeah, you can hopefully figure something out. But you should try and make sure your project is appropriately scoped such that just a single GPU on Colab is more than likely going to be sufficient. There are, of course, many things that you should be doing if you're using Google Colab, which we'll talk about later on when we discuss like practical implementation. But one very important thing, because Google Colab has a timeout, so I think they kill all of your jobs after 12 or 24 hours, I don't remember. So you need to make sure that you're checkpointing your model, which means every so often, maybe every few batches or epochs, you save your model parameters into your Google Drive. So that way you can just restart your session and load the previous checkpoint and resume training. So you can look online. I'll also share some resources of like things that people have done in the past to kind of auto restart whenever they reach the timeout and so on. Anyone else? Yes.
Is there a rough estimate as to how similar a final report and an initial project would be? Because if we're substantially deviating, you're supposed to be black back to the entity.
Yeah, so the question is, how similar the thing that you propose in your project proposal, how similar does that have to be to whatever you end up doing and writing about in your final report? So obviously, when you write up your project proposal, you might get feedback from us that says, all right, this is not feasible, you should scale down and try to pursue this less ambitious idea or this less resource-intensive idea. It's very rare that we will say, just don't do this project at all. I don't think we've ever said, write a new project proposal because this one is not going to work at all. And there's also, since you haven't actually done any work as of now, things change all the time. So you might find that your first idea doesn't work for whatever reason. Maybe the data set is not available, or the models that you thought you could train, you can't actually train, or maybe the source code for some model that you wanted to use is not available. It's very common, by the way. So yeah, things are going to change, but we don't want you to completely just start doing a new project without previously telling us and clearly explaining why it is that you chose to pivot away from your original idea. In the final report, we'll ask you for, here are the things that you changed from your proposal and why you changed those things. So yeah, we expect there to be some deviation, but hopefully not a huge deviation. Yeah. So the proposal grading, the question is, how is that going to be graded? It's going to be based on that thing that you're submitting this week. Yeah, I mean, there are a lot of criteria that we ask you to put into your project proposal, right? You have to fill out all these sections. You have to cite X papers to show that you've done your related work survey. Your proposal has to be this length and so on. So, I mean, many people in the past have not followed those criteria, so we take off points. Yeah, we're not going to penalize you if your idea is like too ambitious or something like that. All right, let's get started. So last time on the iPad, we briefly looked towards the end at this backpropagation example with a recurrent neural network. And this was with just single neurons to make the equations and all. Yeah.
This is not showing on the.
Oh, the slides are not showing?
Yeah.
Oh.
I mean, before it was just a simple explanation. I thought that it was switching this one.
Oh, it's showing the iPad. Okay, I'm glad no one commented on this, and these YouTube people are clearly not watching.
I didn't even notice.
All 12 of you.
That
Yeah, okay, so you didn't miss much, YouTube people. Oh, I see a question. Is there a way for participants of online community to form a group and choose a project? I assume this is referring to people who are not actually in the class, in which case, I don't know, you can maybe find other teammates in the YouTube comments or something. And I don't know if it's a good way, but, or you could do it by yourself. Interesting question. Okay, so now I assume this is on this. All right, sorry about that. So now we're going to talk about a full matrix vector recurrent neural network language model, review the loss function, how this thing is trained, and then start talking about attention. So this stuff should all look kind of familiar. Here we have our same example from before the students opened there. And we've already seen this recurrent neural network language model, right? It has this update equation to compute the hidden states. And we're doing this one step at a time, right? So I compute h sub 1, then I have to compute h sub 2, which depends on h sub 1. We already talked about how when we're doing backpropagation with these models, we have to use something called backpropagation through time to update these w sub e and w sub h matrices because they're used repeatedly throughout at every time step of this model. Okay. And yeah, all of the concepts here should be familiar to you. You should understand, what is a softmax layer? How does it work? What are these word embeddings? Why are they parameters of the model? And so on. So some advantages of this recurrent neural network language model that we talked about before is that, first of all, theoretically, it has no limit as to the maximum sequence length that it can process. Although in practice, we know that it's not going to be able to handle, infinitely long sequences, right? There are problems with the vanishing gradients. There are other issues that we'll talk about today. Another good part about this model is that because it shares parameters, the model size, meaning the number of parameters, doesn't increase as we increase the length of the input. If you remember in the fixed window language model, this is not the case, right? Every time we want to add one more word into our fixed window, we need to make our matrix that's actually doing the projection to the hidden state bigger to account for that. That's not the case here because we're using the same matrices for every single word and hidden state at every time step. So yeah, there's many advantages of this model, obviously, compared to the fixed window language model. There's also disadvantages. So at training time with an RNN, we have to compute each representation in sequence, right? I can't compute h sub 4 before I compute h sub 3 because there's this dependency, right? This WH matrix is used along with h sub 3 to compute h sub 4. So I have to do this one step at a time. This makes things slow during training. And then we've already talked about the problems with the vanishing gradients. And there's another issue with this model as well that we'll talk about in a bit. But before we get to that, just to visualize the training process of this model, remember last time we talked about the cross entropy loss, which is what we use to train these neural language models, where it's essentially just the negative log likelihood of the correct word, the correct next word that we observe during training, right? So with an RNN, the way that we train, and someone asked this last time, is we don't just, so if we want to predict the word books here for the students open there, it's not like we have a separate training example that has just this prefix, the students open there, and the only use of this is to predict the word books. That would be very inefficient, right? Because what if we also want from the students opened to predict the next word there, right? That's also in our training data. Do we really want to do these things separately? That would just waste a lot of computation, right? So the way that we do this is actually at every single time step, we perform a prediction of the next word, right? We can do this because there's this sequential computation. I know that at the current hidden state, I've observed all words up till that point in the sequence and not any words that come in the future. So at any point, I can use any of these hidden representations to predict the next word in the sequence. So if we take our data example, the students open their exams. When I observe the word the, I process it using this W sub E matrix. I project it along with this H sub 0 into this hidden state H sub 1. And now using H sub 1, I feed this into my softmax layer, and I predict the word students. I mean, I want to predict the word students, right? So I train this model with a loss function that says, what is the negative log probability of students here? But we're not just going to stop there. Once we compute this H sub 1, we apply this softmax layer, and then we proceed to H sub 2. So H sub 2 assumes that we have the students as our input, right? So at H sub 1, we didn't know that this representation does not contain the identity of the word students, right? That's what we want to predict. Similarly, this vector, H sub 2, does not contain the identity of the next word opened. So we can put a softmax layer over H sub 2 to predict the word opened. So you can see here at the top, the loss was for students. Then we compute the loss for opened. Then we compute the loss for there. Then we compute the loss of exams. And then our final loss for this entire sequence is just the average of the token level cross entropy loss at every position in this sequence. Does that make sense? So instead of having like, 4 or 5 different input sequences, each to predict the next word given some prefix of this input, we're doing that all at once. And in practice, these softmax layers, they're shared. The softmax is shared across all of the time steps. You can see that we're using the same W sub 2 matrix here to do the softmax. Okay, so you can imagine, because last time we talked about doing backprop, but the loss was only computed on the last time step, right? This makes things a little trickier because now I have a loss at every time step. So you can imagine how those derivatives look more and more annoying. We are not going to derive that, but it can be a pain to implement if you're doing it from scratch. We're not going to be implementing these from scratch, so don't worry about it. But you should at least understand the intuition behind how you would do backprop in a network like this. Yeah, so the update is done after the average is taken, and not just for one sequence, but remember we talked about batch training last time. So in one batch, I'm going to have multiple sequences. So I might have the students open their exams, or I don't know, the chairs in the classroom are bad, many different things like that. And I will compute the average loss over that entire batch, and then I will perform my update. Yeah, so that's a good question. When you're working with these RNNs or transformers, you generally will pick some max sequence length, which is kind of based on how much memory your GPU has and can fit. So you might pick, say, 1,024 tokens as your max sequence length. And maybe you have a batch size of like, I don't know, 128. So you have 128 sequences of 1,024 tokens. Some sequences in your data set might not be 1,024 tokens long, in which case you generally pad them with like these kind of special pad tokens until they reach that 1,024 limit. And of course, you don't want to compute the loss for predicting a pad token. So you can mask out the contribution of that when you're computing the loss. So these are all kind of tricks that people do to train these models efficiently.
So are they limited by just the amount we can put in GPU, but are they like, for example, you can take a sequence of one paragraph, second paragraph, third paragraph, do they have some stuff?
Oh, it depends. I mean, you might want to share the representations from one batch to the next batch. I don't think people actually do this in practice. So in practice, you treat every sequence as independent of every other sequence. There are, of course, methods that try and have some dependency there, but we won't be talking about those. Sorry, I missed what you said.
When you say sequences, is that like you're taking it sentence by sentence? Or like, is there multiple sentences in one sentence?
Yeah, there could be. So the question is, what is a sequence? It's just a contiguous sequence of tokens. It could include multiple sentences, multiple paragraphs. It just depends on your maximum sequence length.
Why would we use like size? If they're just going to take tokens until we reach the max size.
Yeah, but you might have, for example, a document that doesn't have 1,024 tokens or whatever, and then what are you going to do, right? So, yeah.
Does the model also take in consideration the punctuation that we have, like an exclamation mark or a comma?
Yeah, so the question is, does the model take into account punctuation? The answer is yes, all of these models do. The punctuation is part of the vocabulary of the model. So like a period, an exclamation mark, these are all separate word types in the vocabulary. So the model is going to be asked to predict them. So the question is, do we use a separator token to separate the sentences? In this case, the answer is no. Why would we want to have a separator token here? I mean, unless you have some clear reason why you want sentences to be clearly split up from each other that is more clear than punctuation, because usually, you know, punctuation ends a sentence. But yeah, in this case, no, you don't generally do that. So we'll talk in the maybe next week about models like BERT that have multiple segments, not sentences, but segments that are included in their training data, in which case you do want to have a separator token to distinguish those two segments, but that's part of a separate training objective, not language modeling. All right, let's move on.
There are two quick questions.
Great.
One is whether the mechanism for word embeddings will be specified later, or
The mechanism for word embeddings. So in all of these models that we've talked about to this point, the word embeddings here are initialized randomly, right? They're parameters of the model, and they're trained directly through backpropagation using the next word prediction, the cross entropy loss, as the signal to guide the updates of the word embeddings. There are, of course, methods like WordDevec and Glove that give you pre-trained word embeddings that already encode some semantic and syntactic information about these words. And it used to be common to initialize these word embeddings using these pre-trained methods, but that's no longer the case. So we won't actually be covering those methods in this class. Is there another question?
kind of a very quick one? What is J? What does J stand for?
Oh, yeah, so these slides use a different notation, of course, than the last class. You can think of J as equivalent to L from the, it's just the loss of the token level loss. All right, let's move on. So one of the issues that we didn't discuss last time is the bottleneck problem. And this kind of is related to the vanishing gradient issue. The fact in this model is that the current hidden state, this h sub n, in this case h sub 4, needs to encode information about the entire prefix that it's seen up till this point, right? So h sub 4 is responsible for encoding the semantics of the student open there, along with, you know, the syntactic role possibly of what is coming up next. You know, the fact that maybe there should be a noun coming after a plural noun, maybe something like this. This may seem reasonable when the prefix is only 4 words long, but what happens if it's 8,000 words long, right? We're condensing 8,000 words into a single vector and then asking the model to predict the next word. This is asking a whole lot, right? Especially if the dimensionality of this vector is small. How exactly are we going to force all of the important information? We may not even know the important information ourselves, right? Our brains are just processing this 8,000 words and making all sorts of abstractions that we're not even aware about. But yeah, it's a lot to ask out of our models. So there's this now famous quote by Ray Mooney, who's a NLP professor at UT Austin. You can't cram the meaning of a whole bleeping sentence into a single bleeping vector. This has been repeated many times since. I think it was probably like 2014 or something when this quote was made, and it's still relevant today. So, and this is just talking about a sentence, right? Now we moved on from sentences to these huge sequences. It's even more true here. So the idea behind the attention mechanism is that why do we even need, in the first place, to have a single vector representing our input sequence, our input prefix? Why can't we just use all of the previous hidden states, right? Each one of them is encoding some information about what it's observed in the past. So instead of having this final vector here encoding everything about the students open there, the idea is, well, let's just have all four of these vectors be used. All four of these token level hidden representations be used before we compute the prediction of the next word. So we can kind of distribute the information maybe and not force this last vector to contain every possible relevant piece of information. So the way we do this is through an attention mechanism, which was first introduced in 2014, 2015 for the task of machine translation. So we're not going to be talking about machine translation just yet. We will in a couple of weeks. But we'll look at attention mechanisms in the context of the task that we've been discussing for this whole semester so far, language modeling. But the intuition is the same. The idea is that you want to allow the model to look at multiple time steps before it makes the prediction of the next word, not just the final time step. So the way it works intuitively is that we have a single query vector. So this might be, for instance, the hidden state at time t. And we have a bunch of key vectors. So in our example, this could be all of the hidden states before time t, or something like this. And we want to assign a score to each of these query key pairs. And intuitively, a key that gets a higher score might indicate that, okay, we should put more of our attention towards this token that was 3,000 words away, because maybe it contains information about, relevant entity or something that's going to be useful when computing the next word. And maybe we don't want to put so much attention on the word at position like 5,000 because it's irrelevant when predicting the next word, right? So that's kind of the intuition, is attention scores are kind of like judging the importance of each of the things that we've computed in the past before making our final prediction of the next word. So let's just walk through a simple example here. So in this case, our prefix, we've actually advanced one word. So instead of computing the probability of books here, the next word in this example is unwillingly. So the students didn't want to read their books, I guess. So we're going to be computing probability of unwillingly given the students opened their books. And books is the last hidden state that we've computed. So this green thing. And green here means, okay, we're going to treat this as our query vector. So the keys are going to be all of the previous hidden states that we've seen up till this point. And we're just going to use a very simple scoring function, which is the dot product between this query vector and this key vector. So I'm going to take this dot product between this green vector and each of the four red key vectors. So I'll get 4 scores, right? I'll get 4 numbers. These are the dot products. So just like we saw with the, when we're getting the predicted distribution of the next word, we kind of want these to be normalized. It would be nice if we could interpret them as a probability distribution over all of the keys. And so we have a simple solution for this, right? We can just apply the Softmax function over all of these dot products that we've computed. And if we do this, we're going to get a probability distribution over all of these keys. So in this random example, it seems like a lot of the probability is on this time step, the very first one. The model is not putting too much probability on any of these other ones. So once we have these scores, we're going to compute a weighted average of all of the key vectors using the probabilities that we computed here as the weights. So if this was like, say, 0.7, I'm going to multiply this vector element-wise by 0.7. Sorry, not element-wise, just a scalar with a vector, right? So this is 0.7 applied to every single dimension of this red vector. Similarly, maybe this is 0.1, this is 0.1, this is 0.1. So all of these are going to get weighted down by 0.1. I'm going to sum the resulting vectors, and then I'm going to get a single vector that is the attention weighted average of my keys. Right? Does this make sense? Okay, so once I have this, I can connect this attention weighted average to my softmax layer in addition to this hidden state at the last time step, books. So one way I could do that is simply concatenate this vector books with this attention output vector. So now I have, say, an 8-dimensional vector instead of a 4-dimensional vector. Now my softmax layer is going to take this concatenated vector as input and predict the next word. So you can see in this case, so this is what it's showing, this both of these, the last time step and the attention weighted average, fed into the softmax layer to predict the word unwillingly. You don't have to use concatenation. You can add them. You can do whatever you want to compose these two vectors. But you can see that this is not now forcing this vector, this green hidden state associated with books, to encode all of the information about the prefix. Now I have this alternative which lets me focus on different parts of the input as well as just having this final vector. So yeah, this is the original, this is how you compute attention with recurrent neural networks. Recurrent neural networks are where attention was first used. This is also not a sequence-to-sequence model, so I should fix this slide. Yeah.
So the attention output vector, that's a fixed size vector, or is it?
Yeah, it's usually the same dimensionality. It doesn't have to be, but it's usually the same dimensionality as the key vectors.
So
in this recurrent example, yeah.
So how? Oh, okay.
Yeah.
How you use that sign to go?
Mm-hmm.
Where does that come from? Is that pure learning? Or?
Yeah, so obviously it doesn't make too much sense here why the model should focus on the. This was just a random example. But during the learning process, you can actually start to interpret some of these attention weights and kind of get an idea of why the model might have put so much weight on this particular token. Although, as we'll see later, this is also misleading, especially when we have multiple layers of attention. It becomes very hard to track what exactly does assigning a weight to position 300 mean in this case. But yeah.
But this particular component is for the power box, right? This is not long. This is not process working. This is process today.
Right, but if I update my parameters, this is going to change, right? Because the hidden states are functions of the learned parameters. The query is also obviously a function of the WH and WE and the word embeddings, right? So every time I do an update, the representations of the query and keys are going to change. The dot products are going to change. This distribution is going to look different. And ideally, you would want these attention distributions to kind of, I don't know, learn the appropriate patterns to maximize our ability to predict the next word.
Since you're composing the last hidden layer with the attention output, we're kind of giving like 50% weightage just to the last hidden
Yeah.
layer. So that should be like not do that and just use all of them together.
You could do that. As we'll see later in this class, with the self-attention mechanism, we're no longer doing this concatenation thing. But we'll get to that in a bit. Yes.
How are we going from a variable k in attention distribution? Because there's going to be k words before the attention distribution, and that's variable to
Yeah, because we're doing this weighted average, right? So I could have 300 of these red key vectors, and I have a 300-dimensional softmax output, right? So I have weights for all 300 of these key vectors. Then I'm just summing them, doing a weighted sum, right? So it doesn't matter how many there are. At the end of the day, when I'm doing this element-wise addition, I'm just going to get a single vector that's the same dimensionality as one of the key vectors.
The attention distribution part, we don't have like one path vector or anything, right? We have like a single probability. It's not even a vector, right? It's a number.
Yeah, so the attention weights, right? This is just a single number. It's a single number per key. So if I have 300 keys, I have 300 numbers representing the attention scores.
Yes, no, I'm just very confused with how you're jumping from the attention distribution part to the attention part.
Okay, it'll be more clear when I go through it on the iPad. So, yes, last question.
Instead of using books as the query, like the hidden representation of books as the query vector, can we compute the next hidden representation and then use it as a query?
But the goal here is to predict unwillingly. And remember that the next hidden state takes unwillingly as input, right? That's the word embedding that's coming in the next time step. So if my hidden state already has information on unwillingly, it's going to be trivial to predict the next word, right? It already knows what the next word is. It got it as input. So that's a very important thing that we should talk about, is that when you're implementing these models, you have to be very careful not to leak information about the thing that you're trying to predict. As you can see, it can get pretty complicated when you have multiple sequences, and then at each sequence you're predicting something at the next time step. So you're doing multiple predictions per sequence. It can be kind of easy to mess up and make an off by one error or something, and then your model is doing really well, and you learn that, oh, well, it's just because it's cheating, essentially. It knows exactly what it's trying to predict.
The hidden state, is it combined with the input later, or it's combined first and then we make the hidden state?
So if you remember the recurrent neural network update equation, which is here. So this h sub t, you can see, is a function of the previous hidden state as well as the current word embedding. So both of these things have to be combined before we get the hidden state for the current time step. All right, let's just move on. Maybe you can ask in a bit. Is it a quick question?
Sure. When we in the diagram that you had, do we factor the attention part as well?
Yeah. So you can imagine if you're writing out the equations first. Now we've added this thing on top. It becomes increasingly more annoying to compute these things. When I was in grad school, we had to do this by hand, so it was really not fun. But nowadays, none of you have to do this. So, but yes, you have, your cross entropy, the loss that you compute is a direct function of this attention vector as well as this. So the loss, when you backprop, it goes through both this path as well as this path. Yes, and you can see how this also helps with the vanishing gradient problem, right? Because now I kind of have a shortcut to any potential state in the past. I'm no longer just biased towards the more recent ones. Like if I put all my attention probability on position 5,000 away, the gradient is going to flow directly through that and bypass all of these hidden states. All right. If we want to compute the next prediction here, we're going to use this unwillingly hidden state as a query. This books should also be a key vector. I should really update this slide, but this, there should be another arrow from unwillingly to books. Books should turn red here. Essentially, you're just doing the same thing, except you have a new set of attention scores. All right, so here we can see how attention solves this bottleneck problem, because now we can just have these shortcut connections to various previous time steps, not just the most recent ones, which are our most recent time step is kind of biased towards. Similarly, it helps with the vanishing gradient problem, right? Because now I get this other path to these far away time steps, not just the one associated with the last hidden state. As I also mentioned, it can provide some interpretability, especially with the early machine translation single layer recurrent neural networks. You could even see these kinds of alignments emerging between like English and French here in this example. But as we'll see later in the semester, this is basically no longer true for the modern huge models that we have now. All right, and we just talked about the dot product as our scoring function, but there are many different other methods that have been proposed. So the original formulation of attention in the paper that I think was your reading was not actually a dot product. It was you concatenate the query and key vector, project it using some learned matrix, then multiply the result with or take the dot product with a vector to get a single number. So it was a little more complicated than just a single dot product. This is because you might want to get additional parameters into your attention scoring function. Specifically, maybe this W1 is now a new learned parameter associated with the attention. Many other things proposed. We talked about the simple dot product. The one used commonly today in the transformer model is a scaled dot product. So we'll talk next time about this and why you might want to use this. Okay, so before we get to a more kind of iPad example, their attention has more uses than just being a way to avoid this bottleneck problem. You can also use it to implement what's called a copy mechanism. So let's say I have this input, Fed Chair Janet Yellen, maybe 500 words go by, raised rates, period, miss, and then you're trying to predict the next word. So here, maybe the ground truth next word is Yellen, referring to this entity that appeared way in the past. And the way that we would do this prediction using all the stuff we've talked about till this point is we put this hidden state into our softmax layer, and then it has to predict Yellen out of this huge vocabulary of all the other word types. But maybe you're in a data set and Yellen just doesn't occur that many times. And so the model doesn't realize that, okay, this is something that needs to be predicted. Maybe it doesn't even occur at all in your training data set and it's replaced with an UNC token, unknown token or something. So attention you can use as a way of copying things that you've seen in the same document instead of having the model predict it using its softmax layer. So for example, if I compute attention using this hidden state on this as the query and all of the previous hidden states as keys, maybe I get this distribution that you see with this these green bars where the probability of Yellen is quite high. So if I have a model that is trying to copy things that it saw in the past, I could just say, okay, with this probability, I'm going to copy the word that was in this position in the input document. I can interpolate this probability with what my softmax is giving me. So these are these blue bars down here. So you can see it gives some probability to Yellen, but it also gives probability to Bernanke, who I guess was a previous or subsequent Fed chair. And so if I do some sort of averaging or between the copied probabilities, which is just the attention distribution, and the softmax probabilities, I will upweight Yellen and downweight Bernanke. So this is good for me. All right, any questions?
So technically can look backwards, but we can still look fully arithmetic dependent on our sequence length. If we have a higher sequence, then it's dependent on something with previous sequence.
Yeah, so the question is the attention can only look back until the beginning of the sequence in which the example is associated with. Yeah, so that's totally true. Yes?
So we have two different attention mechanisms, one for copying and one for prediction.
No, sorry. I mean, in this case, so you can, in this case, it shows you that there's two different, sorry. So yeah, in this case, It doesn't show you the attention distribution to compute the hidden state, but they can be the same. So this attention distribution can also be used to feed into the softmax layer as input. But this is just another way of using the attention to even more explicitly influence the final predicted distribution. Yeah.
G is the learned parameter, right?
Yeah, so G here appears to be a scalar. I think in this case it's a vector actually, so there's one element of G for every, actually I don't know, it could be a scalar that's just like an interpolation value. So with some probability I'm going to rely on the attention distribution, some probability I'm going to rely on the predicted softmax output.
So is it like an anchor parameter or is it like?
No, it's usually learned. So, and it can be dynamic, so it can change depending on whatever this hidden state is. It could be a function of the hidden state. It says at this point, you know, if I see this title, I might be expecting a name of a person. If I want to predict a name of a person, I might just want to copy it from the context rather than predict it explicitly like this. So yeah, it's usually dynamic. I actually think it's a vector in these examples, but in this kind of model, but I would have to double check.
There's one more question to follow up about the word embeddings.
Yeah.
So whether they are being updated after each batch and then a retreat for the use for the next batch.
Yeah, so the question is, when we're training the word embeddings, do we update them after every batch along with the other parameters? The answer is yes. So you can imagine if I have a vocabulary of size 10,000, so 10,000 word types, I have a matrix that contains all of these word embeddings. It's going to be of size 10,000 by whatever the dimensionality of the embeddings are. So maybe say 100. This is a model parameter. So at every batch, I'm going to update some subset of the rows in this matrix that correspond to whatever word types appeared in that batch. And then for the next batch, I'm going to use the updated word embedding matrix that I backpropped through in the previous batch. So yes. Okay.
How do we have the ambiguity here? Words with same words with different meanings, words with multiple meanings?
We're not handling those in any special way. So, you know, like a word with multiple senses, for example, is not, there's just one word embedding for that word.
According to the bottom formula, are we taking attention as well as the softmax?
Yes.
So is it the attention output fed into the softmax?
So it's a little confusing. The attention output here, so these two distributions are of different dimensionality, right? So this pointer one, the one in the green, it's the size of the input sequence that you've observed so far, right? Each of those is getting a probability because it's computed through the attention mechanism. Meanwhile, the softmax RNN, this one is computed by our normal, like, it's full vocabulary, right? Maybe this one is 10,000 items, and this one is only 300, or whatever the sequence length was. So to do this addition, they need to be the same size, right? Otherwise, so what we do is, let's say, so essentially I take this attention distribution, and I kind of, so I take, say, 10,000 dimensional vector, which corresponds, each dimension corresponds to every word type in my vocabulary. Then I look at this attention distribution, and for each position I see, okay, there's some weight on fed. Let me add this weight to the position of fed in my new blank, like 10,000 dimensional vector. Oh, I see some probability on Yellen. Let me add, so I basically create a new distribution of 10,000 word types out of this attention distribution that I have. Then I can do that addition. So if a word occurs multiple times in the sequence, I'm going to be adding the probability of both those to. Yeah, it's a little confusing, but in general, these days, these kinds of copy mechanisms are also not used. So don't feel bad if it's too confusing or whatever. We're not going to test you on this. All right, let's move on. Oh, okay. I doing here? All right, so I want to, whoops, do this. I assume this is visible on, oh yeah, sorry, I have to do this too. Okay, so everyone can see this. All right, so we've talked about attention in the context of recurrent neural networks. Now we're going to get to the core component of modern neural NLP models. That's self-attention. Okay, so let's just take our old example. Maybe students opened there. And in a recurrent model, I'm not going to draw this h sub 0. We have this. Sorry, I'm going to move this down a little. And then at each time step, I'm going to predict opened, predict there, and predict books. I guess in the actual example it was exams, but we're going to go with books. So one thing that makes us slow during training, as I've said many times now, is that these connections here make me compute all of these things in sequence, right? So if I can get rid of recurrence at training, I can compute all hidden states, h sub i's, in parallel. And this would be great. I will be much faster during training at computing my loss and doing backprop and so on. So the goal, oh, okay, maybe how do I do this? Probably a bad idea. So let's see. Our goal might be that we want to create something like this, where we don't have these dependencies between the different hidden states. And if we don't have that, then we can compute all of these in parallel. So these things we called h1, h sub 2, h sub 3. Here, just to be clear, let's just call these by different things: z sub 1, z sub 2, z sub 3. And so we are going to compute these z's, which are kind of equivalent to the hidden states. I'm just going to call them z to avoid confusing them with the recurrent neural network computation. We're going to compute these using a mechanism called self-attention. So, how should I do this? All right, I'm going to go to the bottom of this page. Let's say we start as before. Students open there. The first thing that we're going to do in self-attention, at least the way that it's used in transformers, is we're going to compute 3 different projections of each of these word embeddings. So for students, I'm going to compute, let's see, I'll use blue, a query vector, let's say q sub, I'll do that later. And this, we're going to compute a key vector. We're going to compute a value vector. So now, I feel like it's actually slower for me to use this tool than the draw it over and over. Maybe not. And for this, I'm going to say these are the value vectors, the key vectors, and the query vectors. So in the recurrent neural network, we saw that the query vector was just the hidden state from the final hidden state. The key vectors were all the previous hidden states. In a world where we don't have that recurrent hidden state computation, we have to make up these queries and keys ourselves. So how we compute these query, key, and values is, let's also name our word embeddings. So this was C1, C2, C3. So Q1 is just some function, maybe tin-h or relu or whatever, of WQ. This is a weight matrix associated with the queries, C1. Similarly, for the key vectors, we're going to use W sub k or W sub v for the value vectors. So we have 3 different weight matrices that are used to project the embeddings to query, key, or value space. And these matrices are shared across every position in the sequence. All right, so we've done this. Now, what is the purpose of doing this? The idea is that we're going to compute our attention weights now using these query and key projections. The value projections are going to be what actually gets averaged to compute the final z vector associated with that time step. So let's start at the last position here, the C sub 3 position associated with the word there. So I want to get attention scores, and I already have computed the queries and keys. One difference between self-attention and the attention mechanism in a recurrent neural network is that the key at the current position is also used in the computation. So in a recurrent neural network for position 3 here, I would take Q3 and I would take a dot product with K1 and K2, right? In self-attention, that's no longer the case. So I'm going to take Q sub 3. So essentially, I'll have 3 scores. Q sub 3, K sub 1, right? This is the attention score associated with the very first key vector. I also have Q sub 3, K sub 2. And I have Q sub 3, K sub 3. So the time step itself is also associated with an attention score. And note that our goal here is to predict the next word books, right? So this embedding at time step 3 has no information about the actual next word. So this is fine. We will get to, in the second and first time step, how we prevent leaking information about the future. So I have this, right? And these are all, let's just say, dot products for this example. Now, these are, unnormalized scores, right? They could be any real number. So what do I do to convert this to an attention distribution? Yeah, so I'll just wrap a softmax around this. And so now, maybe I get something that looks like this. So this could be Q3K1. This could be Q3K2. This could be Q3K3. So let's say this one is like 0.3, this one is 0.5, and this one is 0.2. So now, in the recurrent neural network, I would just use these scores to compute a weighted average of the key vectors themselves. But in this new formulation, I have these value vectors, which are additional parameters. And so I'm going to actually use these scores to compute a weighted average of the value vectors. So maybe I'll write that now. Use attention scores to compute weighted average of value vectors. So what that means is if you remember here, this is a z sub 3, the thing that I eventually want to get. Z sub 3 is going to be equal to 0.3 times v1 plus 0.5 times v2 plus 0.2 times v3. So all of this is going to give me some vector which I will use to predict the next word, books. All right, is that clear? Does this maybe, okay, well, after we do another time step, hopefully it'll be more clear how this weighted average can apply to sequences of variable lengths. So now let's take a look at the second time step here. So in this case, we have a little difference from the previous example in that I can't just compute Q2 with V3, right? Why is that? Or sorry, I can't compute Q2 and K sub 3 as part of my attention distribution. Why is that?
Yes, because it will be leaking information from the
Exactly. So K sub 3 here already is a function of the word there, which is what I'm trying to predict at the second time step. All right, so let me do this again. Okay, so at the second time step, what am I going to be computing? Q sub 2, K sub 1, and Q2, K2, right? So I have just two scores here. Maybe I have 7.3, and my Z sub 2 is going to be 0.7 times V1 plus 0.3 times V2, and then I get some vector, and I'm going to predict there. And so with the, yeah. So the question is, how do we get this word there? So when I say predict there, I mean we pass this vector z sub 2 into the softmax layer, right? And we talked about the softmax layer. It has its own matrix that projects this to the size of the vocabulary. So that's what we're doing. And then we're hoping that the model assigns high probability to there after putting it through the softmax layer. Any other questions?
What is the intent behind values?
That is a great question. It's very hard to say. There have been papers since the introduction of this framework that show that you can just drop the value vectors and do this average on the key vectors, and you don't lose that much performance. You barely lose any, if at all. I think the original intuition was perhaps it's just another way of adding parameters to the model, because now we have this W sub V matrix as well. If you have a lot of layers in the model, you can have a separate one of those per layer. I can't really answer the question because it's very unclear if it even helps or not. But this, for better or worse, is what people use these days. So yeah. Any other questions? Yes.
Since you remove reference, so ideally this is nothing but a fixed length neural network. And instead of using the entire procedure which you are using, you could just stack multiple layers of neural net and let this learn by itself and come up with the final solution.
I'm not sure I understand.
So my question is, like, we are doing reference. We are just using the embedded information code and we are trying to project it into our C1, C2, C3. And we have defined the procedure for developing C1, C2, C3 with the attention. Now my question is, like, why not we define it explicitly and just we could have
you mean
multiple layers of neural net and
yeah, so there is a lot of work on the question is, why did we define these equations in this way? Maybe we could have let a network learn the optimal computations for all these representations. There's a lot of work on kind of automatic architecture search to find the best architecture without specifying it ahead of time. So it's basically a search, architecture search, where you specify, okay, I want to explore these different hidden, these different composition functions, or there's recently a paper about just using all the TensorFlow primitives as potential modules, and then some algorithm would find the best combination of all of those. So if you're interested, you can look into neural architecture search. But okay, let's finish up here.
There's one question.
Okay.
Okay.
Is it short? Because we have...
Yeah, I mean, like, do we keep all the Q, K, and B values, or do we delete them after each batch?
Oh, so the question, we don't delete them, but wait, what, okay, so, the Q, K, and B are specific to the inputs for each batch. So if the question is, do they persist across multiple batches, the answer is no. They're always different for different inputs. All right, we will just finish this up because there's one more important thing that I want to show you. So first, of course, no Q2, K3 because of cheating. Highlight that. And then you can also imagine doing the same thing for the first time step, right? There's only one attention score. The probability is 100% on this first value vector. It's quite trivial. Okay, so what is interesting about this new formulation? There is no dependency between the z's, z sub 1, z sub 2, z sub 3. I don't need to compute z sub 1 before I compute z sub 2, right? Like I would in a recurrent neural network. All right, so let's see now how we can compute all of these things in parallel, which is a true advantage of this formulation over the transformer. And we have 10 minutes-ish to do this, so I think we can do it. How can we compute z's in parallel? And some of you might have already caught on to this. It's quite straightforward. Let's say we have our query vectors q1, q2, q3, and our key vectors we'll just write out the attention computations again. So our attention scores are here just Q1, K1. Maybe we'll call them A. A2 is Q1, Q2, K1, Q2, K2, A3, Q3, K1. So I can, if you imagine putting these things into matrices, so if I have a matrix here, Q1, Q2, and each row of this matrix is one of my query vectors, and I have a matrix of my keys, where the keys are columns. And I do this matrix product here. Here I've just shown the dimensionality of these vectors to be 4, I guess, for this example. The resulting matrix is a 3 by 3, where the rows, this should be a key. And each of these elements in this matrix is one of the dot products that is used in these attention distributions, right? So let me go ahead and copy this. So if we actually look at this, if we look at this, we can see that the attention scores, these A1, A2, A3, they're just subsets of the rows of this matrix. So for A1, I'm interested in this cell, right? For A2, I'm interested in these 2 cells. For A3, I'm interested in all of these 3 cells. The remaining cells of this matrix, these are the ones associated with cheating, right? They have info about the future words. We need to exclude them. And so the way we do this, maybe I'll go down here. The way we do this is to use a mask matrix. And this mask matrix will eliminate these undesired cells from the computation of our attention scores. So specifically, if we have a 3x3 mask matrix, we're just going to put a 1 in each of the cells where we want to preserve the value. And in these, we're going to put a negative infinity. So the reason is we want the value of these cells to be 0 after we compute the attention scores, right? So if we go up here, in this case, we want a 0 value to be on Q2K3, right? The thing that actually has some cheating going on. So we can accomplish this by setting these cells in the mask equal to negative infinity. Why is that? Yeah, that's right. So after I apply the Softmax function, all these cells with negative infinity in them will go to 0, which will give me the desired distribution without cheating. Yeah.
If the dot product is negative, then multiplying it with negative positive and a very negative.
Yeah, you just want to turn all of those cells into minus infinity. So I think the actual implementation is not a multiplication, but first you probably multiply with 0 and then set the cells that are 0 to negative infinity, something like this. Yeah, that's a good point. So anyway, the negative infinity output goes to 0 after Softmax. And this is called a mask matrix. So that, yeah, as you said, the actual implementation is not like this, but this is just the intuition.
Maybe add 0.
Yeah, you could do that too. Okay, so after we do this, at the end result is these. Okay, so final result. Whoops. These become 0 in the attention distribution. Now I can compute all of the attention weighted average also through a matrix multiplication using this matrix, which contains all of the attention scores. So you can see that I computed all of the z's in parallel just by using these matrix operations. There was no dependence between z1, z2, z3, which allowed us to do this, right? Well, I can't do this in an RNN because of the sequential dependencies between adjacent time steps. And I can, okay, last thing, I can only do this during training. I can't do this at test time if I'm predicting the next word. Why is that? So I can only compute all of these z's in parallel at training time, but not test time. Exactly. So during training time, I already know the ground truth sequence, right? That's how I'm training the model. At test time, I don't know what's going to come next, right? So I don't have the full sequence. I have to proceed word by word. So at test time, there's no benefit to a self-attention-based model over a recurrent model. Both of them have to go word by word. It's at training time where they differ. Because I have full knowledge of the input sequence, I can completely parallelize the computations of these z's at training time in a way that I can't do with a recurrent network. So if that doesn't make sense, you should think about it more and read more and look at this until it makes sense. All right, so next time we'll be talking about the transformer, which builds upon the self-attention mechanism, but has a lot of other things going on as well.